And because of that, we're going to make a little adjustment in not how much we're going to cover, so we're going to cover the amount. But my philosophy has always been, if I'm going to hand out homework, I want to make sure I go over number one. I'll always give you a chance to answer or ask questions, so I can answer questions so you know exactly what's going on. So that would mean, all right, here's the notes, and then hopefully you have your homework done by the next day, ask questions. And what I've been doing is trying to, cut off that problem before we actually get to it by doing examples of the kinds of questions you see in the homework prior to you doing the homework, so you have a guide to guide you. Now, if you haven't touched the homework yet, well, that's the other catch-22 of not making the homework do it until the day of the test. You're going to get to that day of the test, which hasn't even been set up there yet, but do you still remember what we've done? So, I know I need to go faster. That means I need to cover fewer examples during class. I need to adjust the assignments. I'm trying to make them shorter. That means I can't expect you, I'm going to do it right now for section 5, 6, and 7. If you have already started all those, well, but this is what you'll be held accountable for. Right? Unfortunately, I still need to readjust section 7, but I'm readjusting, I did readjust 5 and 6. And I'll show you the difference. I haven't been able to make copies. Well, first of all, I'm not done with 7 yet. But I couldn't make copies even if I wanted to, but it seems like the school is out of paper. So I couldn't make copies if I wanted to. I'll have copies for you next Tuesday, even if I gotta go, somewhere and make the copy myself. But this is the old homework. Okay. And again, I'm gonna make adjustments on 5, 6, and 7. Difference. And I will post the new assignment in Canvas, and I will email it in Canvas to you. So at least you have it as a handout if you don't get it as a printed out until next Tuesday. So 1-5. So 1-5 was 1, 2, 5 through 17. It's now 1 to 15, 17, 19, 25, 33, 31, 37, 41, 49, 71, 73, 75. So I just handpicked it. Okay. And again, I'm going to post it, or if you want to take a picture of what's up there now, you can certainly take a picture. Pictures are quicker than writing things down these days. Section 1.6, and let me, for those of you who don't even want to take a picture, I'll even zoom in for you. 1.6, some of it is a little tiny bit the same, just a tiny bit. Maybe 5. Sorry about this. I want to double check something. That's why the screen is poor, because pull too hard. I'm still not sure we're doing this. Yeah, so it was 1931. I included 35 because it's actually a pretty good problem to do. But then it doesn't go all the way to 51. I kind of picked and chose random problems in between, not random, but problems with purpose. Oh wait, I'm looking at the wrong thing one. I'm looking at this one. It's that one up there. So instead of 41 to 61, just doing 1, 2, 3, 4, 5 questions there. Instead of going all the way to 87, just do the 81. And then to be edited is section 1.7. Okay. So I'll get that finished up and emailed and posted hopefully tonight. Hopefully tonight. But I'd rather not do anything this week. Okay. No, that was not on time. So we have 1.4, just I think just bare bones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that's better than Tuesday. I don't know where everybody is. Not everybody. Whenever I say that, I'm like, what about the people who? Yes, he does. He does. Count more than the people that want. Actually, we're able to count. Okay. So from 1.4. We are picking up with these last examples. Choosing and using 59, 4, 61. Then I'm going to show you 63, 65, and 73. And then you're going to choose 75 and 77. And then we're going to do 79. And then you're going to choose 81, 83, or 85. And then we're going to walk and talk it. 99 because it's basically matching through 104. Okay. So 59 or 61, what do you want to see? 59. Okay. You're supposed to graph this by hand. It's a piecewise function. It's got 3 pieces. And when you have a piecewise function, piecewise, pieces, do one piece at a time. We have f of x is equal to the function, the first piece is x plus 3 when the x's are less than or equal to 0. So that means negative numbers or 0. The function is equal to exactly 3 for every x value that's greater than 0, but less than or equal to positive 2. And then for all the x's that are greater than positive 2, the third piece is 2x minus 1. For all the x's that are bigger than, to the right of, positive 2. Now, the good news about this problem is that those three pieces are all linear. They're all nice lines. So the first thing you want to look at is what bounds one function from the other. When does one function stop and the next one start? So basically, it's these explicit domains. The function is separated. The pieces are separated at 0, and then the next piece is separated at 2. So your break apart numbers is here at a 0. And on this side, for all the x's that are to the left of 0, so right above this part of the graph, for this part of the graph, for all the x's that are less than or equal to 0, remember what this f of x function represents. It represents y. Y is equal to, on this side, just x plus 3. That's what's happening to the left of the 0. Then the middle piece, the next piece, in between 0 and 2, and I'm sorry that it's so small, but in between 0 and 2, for all the x's that are bigger than the 0, but less than or equal to the 2. F of x equals 3, but again, that means that y is always 3. And then over here, to the right of the 2, for all the x's that are greater than the 2, the third piece, your y's, are going to be equal to 2x minus 1. Now, it's like having 3 houses that live next to each other. Each piece is its own separate house. And these houses, they all have one fence in common. Now, here's the deal. One of those houses actually built the fence, and the other house didn't. Whoever built the fence gets to sit on the fence. Whoever didn't build the fence, they can only get really close to it, but they better not touch it. It's like you have a neighbor, and your neighbor's going to get really ticked off if you sit on their fence. If you have an equals, you own the fence. That means when I plot your graph, you're going to have a solid point at that number. If you don't have an equals on the number, then you don't own the fence, so you're going to have an open circle when you plot that number. No equals, open circle. If you have an equals, closed circle. So here's what's happening. On the left-hand side of 0, for everything to the left, less than or, let me use green, less than or equal to 0. The nice thing is that's a linear equation, x plus 3. But it's not a complete line. It's not just from negative infinity to infinity, because if it was, The y-intercept would be 3, the slope is up 1 over 1, you graph a line like this, but it's not. It's only the left-hand side of it. And some of you are going to be fine trying to do it that way. I'm showing you, give me 2 points for a line. The first number you want to plug in, the first number, is the fence. You always start with the fence. The number that separates your two graphs. I'm going to start with plugging in 0. I'm going to let x equals 0. And I'm plugging it into y equals x plus 0. Now, because there's an equals, less than or equals, when I plot the point, it's going to be a solid point. Or actually, they use the word closed. It's going to be a closed point. So, y equals 0 plus 3. Hey, that's a 3. So at x equals 0 and y equals 3, right here, I get a closed point. Now, I keep telling you, this is the first time we've actually graphed by hand for a while. You have to plot and label. If you just plot it, that's not good enough. I don't care that the number line is already numbered. If it's on the x or the y axis, a single number is perfectly fine. You don't have to use an ordered pair, because I have too many students that get it back. Instead of putting the correct answer, 0 then 3, they put 3 then 0, then I got to take off points. And I don't like taking off points if I don't have to. So this is exactly at 3. It's like labeling a number line if you were going to. Then, usually people pick something over here and they plug it in, but you can't go in the other people's yard. You have to stay in your own yard, and your own yard is only x's that are less than or equal to 0. So you got to pick a number on this side of 0, and because it's allowed, you pick anything you want. I'm going to pick something a little bit, further away, because if I just pick -1, it's a little close. I'm going to pick -5. That's my choice. So y is equal to -5 plus 3, so I get -2. So when I pick -5, the y value is -2. Here, and then it's like that. Whenever you have a point that is in one of the quadrants, you have to label it with an ordered pair. Parentheses, this is -5, -2. So the first part of our graph connect these two because it is a linear graph, and you just go this way only. Make sure you put an arrow because it will go forever to the left. Okay? So that's the left house. The house in the middle. The house in the middle. Okay, and because I don't have room in the middle to do the work, if 0 is less than the x, which is less than or equal to the 2, then y is always a 3. The first number you're going to plug in is 0. You always plug in the fence. You always plug in the fence. Because where one house stops, the next house begins. Okay? Where one stops, that next x value, that's where it's going to begin, the same x value. One is going to be a solid point, a closed circle. One will be an open circle. So here's the deal. When I let x equal 0, because there's no equals on that 0, it's going to be an open circle or an open point. And hey, look, when y is always 3, no matter what I plug in, there is no place to actually substitute x into the equation. So y is always a 3. Now, it just so happens that's the exact same coordinate that the last one left off at. So the middle house is basically going to pick up where the last one left off. It's going to still be a closed circle because for the graph, for the overall picture, it's a solid circle. But for the part in the middle, it's where that graph would be if you could plug 2 into the graph for the middle part. You got to have something. Okay, that's where it would start. What else do we want to do? We need 2 points because that's a linear equation. Since it's the middle part, it has a left-hand side and a right-hand side, basically a finite interval, It doesn't go from negative infinity or anything like that. So you can go from the left-hand side fence to the right side fence and just connect those two. I'm gonna go to the 2. If I let the x equal a 2, well, y is always 3. But here, when x is 2, there's an equals. So that's going to be a closed point. When I plug in 2, the y is a 3, and that's closed at that ordered pair. Because the middle house owns the fence on the right. Well, here 2. There's a closed one in blue, and it just goes horizontally straight across. So that's what the middle house looks like. And then the house on the right, first number you're going to plug in, for all the x's greater than 2, we're going to start with let x actually equal 2. But when you plug in 2 here, because this right-hand side house, the right house, there's no equals, this would be an open point. If I plug in 2, I get y equals 2 times 2 minus 1. So y is 4 minus 1, so y equals 3. When I plug in 2, I get 3. For the right-hand side, well, yeah, that means it's an open circle right where the middle house left off. This is not always going to happen. This time it did. And that one's going to start where the last one left off. And now I just need one more point because that's also a linear equation. So now I just got to pick another number to the right of the 2. Or if you can see the slope, you can just use the slope. But I'm just going to pick 6. Let x equals 6. I get y equals 2 times 6 minus 1. So I get y equals 12 minus 1. I get y equals 11. So when 6 goes in, we get 11. When 6 goes in, we get 11. Right there, 6 comma 11. And on the right-hand side of this house, it does this. Don't forget that arrow. Okay. 3 pieces, 1 piece at a time. And if you notice, when I did the right house, I didn't even look at the left house or the middle house. Stop, I was done with it. When I was doing the house on the left, which is a horrible movie, not a horrible movie, but it's just like a really depraved movie if you ever want to see that. Just don't, never mind. I said, when you're working on this one over here, Didn't even think about the other ones. One piece at a time. Okay. All right, 63. Okay, use a graphing utility to graph the function and determine whether it's even, odd, or neither. Neither. So y equals 5. That was x equals 5, so y equals 5. Just move that over this 10. I know I'm shrinking things. So, window check. I'm gonna make it, if it's even, whether it's even or odd, it's about f of x and f of negative x. X, negative x, x, negative x. 5, negative 5. 3, negative 3. 2, negative 2. 27, negative 27. It's about left side, right side. One's positive, one's negative. So right now, my window, -4, +3. That's not a good window if you're trying to see whether or not it's odd or even. You want to have whatever's on the left to be equally represented on the right. So I'll just change it to -4 to 4. And anybody know what this is going to be a picture of? F of x equals 5. Nice. What kind of line? Horizontal. Okay. My y min and max negative. I mean, if I just graph this right now, look at how big it will be. I mean, that would be good enough, but if I try to do a zoom fit, that's really not going to be much help either, because it says window range error. The calculator, when you do a zoom fit, it's going to arrange the window on the y-axis to give you a perfect picture, perfect y window that represents everything from the negative min, x min to the x max. Since everything is a 5, then your calculator thinks that your y window should go from 5 to 5, which gives you no window at all. Because that would represent all the y values, 5 to 5. Nothing at all. This is why you need to know what you're looking at in the first place. So you need to do your own windows. So, see, 5 to 5. So I'm going to change my y minimum. I'm going to change that. And when I set up a max or a min, I like to see the y-axis if I can. So I'm going to pick something below the y-axis so I can see the y-axis in my picture. And if I just pick 5, I'm not going to see the graph because it's going to be up there at the top. I won't see it. So I'm going to pick 7. There we go. Now, even functions. Here's the characteristic of even. F of negative x is equal to the same answer as what f of x would be. It's basically reflected actually the word they use is symmetry. Symmetry about the y-axis. So what's on the left-hand side of the y-axis should be on the right-hand side of the y-axis. If it's odd, then f of negative x is going to equal the opposite of the f of x answer. So it's going to have symmetry about the origin. And I'll be a little more specific about that in a second. So over here, when you plug in 1, we get 3. When you plug in negative 1, we get 3. When you plug in 3, we get 3. When we plug in negative 3, we get 3. Are the y values on the right side the same as the y values when you plug in their counterpart on the left side? Yes or no? Yeah. For every positive x you plug in on this side, over here on the negative value of those x's, you're going to get the same because all the y's they're all 3's anyway. So no matter what you plug in on the left, you're going to get the same y value on the right. For every single x that you can plug in, the f of the opposite side is going to be the same as that y value. When you have symmetry about, not on camera, when you have symmetry about the y-axis, that means if the original graph is xy, then you'll also get if it's even, when you plug in negative x, you'll get the same y value out. The y values are the same. And that's if you plug in, it has to be same distance away from 0. That's the reflection across the y's. If it's odd, symmetry about the origin. So whatever's happening up here would be reflected twice, across the y-axis, then across the x-axis. If it's happening over here, you go across the y, then across the x. If it was over here, you go across, like you go across the y, then across the x. So basically, let's think about a diagonal. If the original is xy, then when you plug in negative x, you'll also get, when you plug in the opposite, you're going to get the opposite of your last y value when you plug in the positive. You're going to get negative y. If you change the sign on the x, the y also changes. That's for odd functions. That's what this means. If I change the sign on the x that I plugged in before, then the y comes out as an opposite sign. And if it's even, if I change the sign on the x, I get the same y value. Don't change the sign. So that was 63. 65. 3x minus 2. So 3x minus 2. So let me adjust my window to zoom fit. Okay. Even. Is this reflected directly over here? No, not even. Odd. Is it reflected over here and then flipped down here? Maybe. Maybe. Let me do a Y scale so we have something to compare. I'm going to do a Y scale of 1. And then I'm going to do graph. Now, you remember this X scale counts by ones, and the Y scale counts by, sorry, the X is counted by ones, -4 to 4. And the Y's are now one little notch every 1 unit. But you can see how, because there's so many more Y's than there are X's, it's not to scale. The distance for a 1 is not the same as the distance for a 1 on a 1. So the way you can now make this nice, because I did a zoom fit before, you can now make this really nice if you do a zoom square. So option 5. And that'll square everything up. And that's a little bit better. It's still, I don't like it. I don't need that much graph. I don't need that. Come on. That's too much graph. What's my window? -18. I don't know. I'm going to make this. Let's go. -3, 3, 1, and then I'll go zoom split. See what happens there. That's still too much. Maybe -3. So 3 here. Okay, that's better. And now if I do my zoom square, let's see if that changes it a little bit. There we go. Okay. All right. All right. So -1, -2. There's -3. +1, +2, positive. +1, +2, positive. It looks like to me, this right here is 1, 1. 1, 1. Little pretty good, 1, 1. And if you're not sure, you can always plug it in. 3 times 1 is 3. 3 minus 2, 1. When we plug in 1, we get 1. If it actually is odd, therefore 1 equals 1. If it is odd, then when you plug in -1, you're supposed to get the opposite of that answer. You should get -1. Well, let's look. If I plug in -1, I should get that point right there at -1, -1. Did I? It ain't not. It's neither, neither, whichever way you want to say it. It's not even because when you plug in 1, we get 1. When you plug in -1, we didn't get 1. When you plug in -1, we should have gotten -1 if it was odd, and we didn't. So it's minus. Okay. So there's basically, it's a checklist. Is it even? Look to see if the same y values come out on either side. Is it odd? We didn't get the same y values. Now check to see if it's odd. If I plug in -3, sorry, if I plug in 3, I get something. When I plug in -3, do I get the opposite of that answer? Then it's an odd. Maybe. Maybe you got to do something a little bit more. Never know. And then if you didn't get either one of those answers, either. That was 65, 73. And then you get to choose 75 or 77. 73. 75, 77, the same. Give the coordinates of the second point A if it's going to be an even graph, function f is even, and then B, what would the second coordinate be if you have an odd graph, if the function was odd. So we know that we test for odd and even by changing the sign of the x. So on 73, we would now plug in -3/2. And I believe I need to apologize, but I'm not zooming in on this side. For the audience at home. So when I plug in -3/2, if it's even, what would the y have to be? It would have to be the same answer as it was on the other side. It's even. It has to be a 4. The y's have to be equal to be even. Equal is even. I don't know if that's all that's even. For odd, again, change the sign for your x. That's now -3/2, the opposite of this x. If you change the sign, if it's odd, you would change both signs. That would now be -4. If you wanted an odd function for that one. That's it. It's like, this is where I remember being like, okay, what just happened? Yeah, it is that straightforward, but you got to know what it means to be even versus odd. The y's are equal if it's even, either side of 0. The y's are opposite sign, either side of 0 if it's odd. If you don't get either one of those, it's nice. So 75 or 77, what do you want? 75? So we're given -2, -9. So that means when you take f of -2 in your function, the answer is -9. So A. So f of, we want the opposite of this one. So we would be plugging in the other side of this x, the opposite of that -2. And it has to equal the same as the original. It has to equal the same as the original f of -2. Okay. And it's, again, I know what you may be feeling or thinking because I've been in your seat. Our definition over here, even f of negative x is equal to f of x, but think of it like this. F of the opposite of the original x, opposite of the original. That's when you take a negative, you're doing the opposite of the original. The original x is a -2. Opposite of that x is going to equal the same y value as the original x gave you. The original x gave us -9. So now this becomes f of 2. What's on the other side of 0? If you're at -2, the other side would be positive. What would this y have to equal? -9. It would have to be exactly the same answer as the original in order to be even. So the ordered pair, +2, -9. The y stays the same, x changes sign. Y stays the same, x changes sign. And this next one, for b, if it's odd, both change signs. If xy is on the original, then the opposite of the x and the opposite of the y is now on your other side of the function. You change both signs. So if you have -2, -9 on the original, then the odd ordered pair, +2 is on the other side, and this would now have to be +9. If it's odd. Okay. It's not just memorizing those formulas, but understanding the language, what it means. So yeah. Okay. Determine whether the function is even, odd, or neither, algebraic. Then do a graphically by using a graphing utility to graph the function. And numerically by using a table feature of the graphing utility to compare f of x with f of opposite of x for several values of the x. Okay. So all the calculator stuff, you don't have to show me. That's just to help you verify. But part A, you definitely got to show me algebraic. So if I plug in, they give us f of t. F of t is t squared plus 2t minus 3. So when I plug in positive t, this is the answer. If the f of t function is even, if it's an even function, when I plug in f of -t, I will get the original function f of t. I have to get the original function that I started with. All the y's have to be the same. And here's the deal. I might show, pick a number. I might plug in 2 and then plug in -2 and I get the same y value. Well, that's because you pick -2 and 2. Maybe it doesn't work for 3 and -3, but you only tried the 2's. And so you're walking away going, okay, I got it right. And then you didn't try another number. Who knows? It doesn't work for everything. If you can show that it works for a variable, then you can make a decision about everything. If it's even, If odd, then f of negative t would be the opposite of f of t. So what does that mean to us? That means to us that f of t is exactly, we would get t squared plus 2t minus 3. And when you plug in negative t, if it's odd, you would get the opposite of this. So you would get negative and then parentheses opposite of that whole thing. T squared plus 2t minus 3. And then if you distribute the negative, your f of negative t, if it's odd, would come out equal to negative t squared minus 2t plus 3. So what I just did was I wrote down what I should be looking for. If I'm going to get odd, this is what I would end up on the right-hand side, the opposite of the last y value. If I'm going to get even, I should get exactly the same y value. If you don't know what you're supposed to be looking for, how do you know when to stop? So let's plug it in. If I replace this t with negative t, then all the t's are now going to be negative t. Parentheses, whenever you substitute a negative, do yourself a favor, use parentheses. So that t squared is now parentheses, negative t to the second, plus 2 times this t is now replaced with a negative t. So that's now plus 2 times a negative t. And then you have a minus 3. So f of negative t is equal to, this is negative t times negative t. A negative times a negative is positive. This is positive t squared. Positive 2 times negative t is negative 2t minus 3. Is it exactly the same as the original function? Is it exactly opposite of the original function, or is it neither? It's neither. You know it's not opposite because that's a positive t squared. This is a minus 3, that's a positive 3. So if you did things correctly, I didn't get this. Yeah, there's a negative 2t in the middle, but that's not enough. If it's exactly the same, positive t squared, sure enough, minus 3, sure enough, but the original is a positive 2t, and this is a negative 2t, not the same. So just because the function is power of 2, that doesn't make it even. Okay? Because I bet this graph has been shifted left to right, which no longer puts its vertex on the y-axis. So now that symmetry is no longer about the y-axis. Okay? So this is a needle. Now 79. So 81, 83, or 85. Which one? 85. So 4 times s to the 2/3. I hate when they use s as a variable, because if you're not really, clear about it, s is a white box. G of s. G of S is equal to 4 times S to the 2/3. When you have an exponent that's a fraction, remember you're dealing with radicals, cube roots, square roots, cube roots, fourth roots. So in this case, if it's even, we're supposed to get the same y answer. So if it's even, G of negative S would be exactly the same answer. It would be 4 times S to the 2/3, exactly the same as that one. If it's odd, then G of negative S would be the opposite of this answer, negative 4 S to the 2/3. Just the opposite. So G of negative S. And so I replace this with a negative S. 4 times parentheses negative S to the 2/3 power. Rules of exponents. When you have a rational exponent, a to the m over n, so you have a fraction. The denominator is the radical that you're taking. The numerator is your power. You can rewrite this one of 2 different ways. The denominator is your radical. It's the root. So this is the nth root of a to the m power. And you can do that m power inside the radical if you want to. Okay. So if I had like 27 to the 2/3 power, denominator is a 3, so that's the cube root. And I can do 27 to the 2nd. I can do that first. Well, 27 to the 2nd is huge. I don't want to make a huge number, then try to find what times itself 3 times equals 27. Or you can do this. Denominator is n. You can take the nth root of the base a. After you take that nth root, you can raise it to the exponent afterwards. So it doesn't matter if you take the nth root and raise it to the power inside or raise it to the power afterwards. So I could also do this as the cube root of the 27, figure that out, and then do my square afterwards. The cube root of 27 is nice. What times shall 3 times makes 27? 3 times 3 times 3. So the cube root of 27, that's just a nice 3 to the 2nd, which is 9. Short, sweet, and simple. Okay? So this is 4 cube root of a negative s to a power of 2. And you can either square it first or 4 times the cube root of that negative s and square it afterwards. So let's see. If I do it, this one, there's a 4 on the outside. When you square a negative, when I square a negative s times a negative s, that's a positive s to the 2nd because of squaring the negative. So it's going to be positive s to the 2nd. So it's the cube root of positive s squared, which the cube root of s squared, that's just a radical notation of 4 s to the 2/3. it's exactly the same as the original function. Even if I did it this way, 4 times the cube root of a negative s, that's going to be a negative because I can take out the negative. If it's a cube root of a negative number, the answer would be a negative answer. But I just don't know what the cube root of the s is going to be. I don't know what that is. But the cube root of the negative is an actual negative number. And then you would square it. When I square the negative, that becomes a positive cube root of s to the second. Because I would get cube root s times cube root s, so that gives me s squared on the inside. And there we have the same thing, s to the 2/3. It's exactly the same as the original, so this is an even function. Okay. That was 85. Down, 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 and those 59. 59. And so the walkthrough, 99 to 104. Multiple choice, A, B, C, or D. I always shrink this down because I don't like the little negative space on the left and the right. And you're supposed to match this up. Match the graph of the function with the description that best fits the situation. So they're not actually giving you the equation of a function. They're describing situations. So which of these would be a graph of the situation? And you have a couple of piecewise functions, or sorry, step functions. They're all, those are all finite. The other ones are all finite. So they have beginning and end, beginning and end, and endpoints. That tends to look like it's going on forever. This one, the steps are increasing. These, the steps are coming down. Little things you start to take apart, the difference between one and the other. This picture, it goes up and then it comes down. That's it. Up and down. This has got the same kind of idea, but it ends higher than it started. This goes up, comes down, goes back up. This starts below, but then it goes up. Okay, in a smooth curve. And maybe you want to read through all 6 of them before you start making choices. The air temperature at a beach on a sunny day, the height of a football kick in the field goal attempt, the number of children in a family, over time, okay. The population of California as a function of time, the depth of tide at a beach over a 24-hour period, and the number of cupcakes on a tray at a party. I talked about one of those when first started. I even did a physical thing that demonstrated this picture when we first talked about the parent graph on that very first page. Basically, page one of everything that's happening. Instead of a football, I threw a pin. What shape was it? When you throw something in the slides. And it's a parabola. Which one? 101, 95, 101. Football. Kicks the football, goes up, and it's either good or not. Okay. So 101 is B. Okay. Which one do you think? Let's just go to A. Which one do you think is A? Which one? Well, 99, 100, 102, 103, or 104. Which one is the air temperature at a beach on a sunny day? 100? Maybe.
Was it like all day?
See, that's a good question.
That would be like 102.
Well, it could be.
Or just from like news, like.
It depends on, so it's not real clear about what they mean by all day. It could be 103. Right now, maybe so. Right now, jungle in the air. Let's see if maybe something will wipe it out. Wipe out, wave, beach. Yeah, got it. C, number of children in a family over time. 99. First of all, would you ever have like a half a child? Well, if you could, maybe I'd have, but it can't be a continuous graph. Okay, it would not be a continuous graph. You couldn't have, if this is 1, 2, 3, 4, 5, you couldn't have each, a number of children in between 1 and 2, between 2 and 3. You could have 0 children, 1 child, 2 child, 3 child over time. So after a certain amount of time, then you have your second child. After a certain amount of time, you have a third child. After a certain amount of time, you have a 4th child, but then you stop having children. You're not going to start your family up here with 10 children. Okay? And then you start killing them all. No. So number of children family, 99. So we got 101, 99. 101 is B, 99 is C. Population of California as a function of time. So population of California, if you think about it, starts off and then it comes down a little bit. Or is the population, because right now we're going to have this one take care of this one take care of. Can we only have integers of population? Or are we going to get like numbers in between? Or would it be a nice smooth curve? Probably not. Let's leave that. The depth of tide at a beach over 24 hours. That was very specific. Tide rises, tide falls. I'll give you a hint. Tide means waves. 102. 102, because you have high tide, then you have low tide. And then it repeats, high tide, low tide, high tide, low tide. Exactly, that's one cycle of a cycle. So 102, 99, 103, I'm sorry. 199, 101, 102, and 103 are off the boards. Cupcakes on a tray at a party. 104. You have a finite number of cupcakes on a party, then somebody takes one off. So now you have one left. Take another one off. So over amount of time, they gradually start to disappear off the tray. See it? So 104 is F. So going back, we have air temperature A, top temperature of sunny day, population of California B. And we've done the rest. And we have left is 100 and 103. So air temperature of the beach on a sunny day. Does that mean 103? So let's just say we're there all day. And let's not take into account that we keep hearing about people are leaving California. I'd say this is California and this, no, that's what you said, right? Yeah, that's what you said, my bad. 103 for the beach. Because you're gonna reach a maximum height and it's gonna start to cool off by 5, 6 o'clock, maybe. But not too much. And then the population in California, as time goes on, starts to rise. Okay. I'd say, what else do you want to see from 104? Okay. Section 1. Of course, I believe the one. Oh. Okay. Graphs and their transformations. So if you're on page, I know you're not on, but when you look at the section 1.5, over opened up the book, right on the very first page of it all is your parent functions. Now there's 6 parent functions that you're going to be held accountable for. We talked about quite a few. You got your linear function. Now the parent functions, the analogy is it's like a cheese pizza. No toppings, no extra stuff, just cheese. Linear function, f of x is just 1 times x. No plus b, it's not shifted up or down, it's not flipped around, there's no slope. Slope is 1. Okay, absolute value. 1 times the absolute value of a single x, nothing inside, no plus k, there's nothing moving up and down, there's nothing changing it, it's not worth it. Simple 1 square root of 1x, nothing inside, just simple square root. This is what it looks like. 1 times an x squared, so no x minus something plus a number, simple x squared, and that's something we talked about. We talked about square root, we talked about absolute value, we talked about x squared for the first day. X to the third. Now, if you look at x squared, if you square positives, you obviously get a positive number, but when you square negatives, you get negative numbers. That's why on the left side, right side, both sides go up. On an x to the third, a cube. On the left, on the right side, my left, your right, when you raise a power, if you raise a positive to an odd power, a positive to a power 3, you get positives. But when you raise a negative to a power 3, the y value is negative. So when it was square, they were both positive. But when you have an odd power, a cube, a fifth, a seventh, the negative numbers to the odd powers are negative y values. So what was up here is now flipped down here. Okay. And the last one, a rational function. And again, that was one of the parent functions we talked about in the first day. 1 over x, rational function. Rational means ratio, ratio means fraction. So 1 divided by x, then you cannot plug in 0. So it's called a vertical asymptote, again, what we talked about, vertical asymptote at x equals 0. It's like a wall that you cannot touch, cross. And there's even a horizontal asymptote at y equals 0. Because there's no way that 1 over x could ever equal 0. So it goes on the right-hand side, it gets infinitely close to x equals 0, but it approaches the y values of infinity. Going this way, going for the bigger and bigger x's, the y values approach 0 as x approaches infinity. The y value or the y values get really, really, really small, but they never cross over. They never touch the x-axis. So it never equals 0 and it never equals a negative on this side. When you're on this side and you're plugging in negative numbers, everything's below the x-axis because positive 2 is above over here, negative 2, 1 over negative 2 would be down below. As you get closer and closer to 0 from this side, the answers will be approaching negative infinity each step as you're going down. As you head towards negative 100, negative 200, negative 1,000, negative 1 million. 1 over negative 1 million is negative 1 million. It's below the x-axis, and it's getting really close to the x-axis, but it can't touch it, and it can't equal 0. And that's what the rational functions look like. We're going to take those 6 parent functions, and we are going to move them left and right, shift them up and down. We're going to smush them. We're going to stretch them. We're going to do all sorts of transformations with them. We're going to reflect them across the y-axis. We're going to reflect them across the x-axis. All by changing the signs. Changing the signs and either adding or subtracting stuff. Vertical and horizontal shifts. Now, I will not be using the same notation that the book uses. Okay, I know that they're using function notation, and you can have functions that are called H. But I'm trying to stay consistent with another class that I use or teach that also uses H to call things. So to make sure that I keep my brain in the right place, I'm going to be using H for something. You'll get good. So if we were to look at just simple f of x equal to x squared. X squared is a parabola. That point right there, when you plug in 0, you get 0. 0 squared is 0. When you plug in positive 1, 1 squared is 1. When you plug in negative 1, negative 1 squared is also 1. When you plug in 2, 2 squared is 4. And when we plug in negative 2 squared is also 4. And so the parabola does this. And that's our parent curve. That's our parent curve. If you mess with the x coordinate, you are shifting the graph left or right on the x-axis. You're going to move it left or right on the x-axis. So if I was going to graph f of x equal to, instead of x squared, x minus 2 squared. Now, the most important point that we like to plot first is the 0, is, whatever makes 0. 0 squared. What would I have to plug in for x to make 0 squared? What would x have to be? 2. If I plug in 2, f of 2 would be 2 minus 2, and then you would square it. So f of 2 would be 0, and then you square it. So f of 2 gives you 0. When the 2 goes in, 0 comes out. So it's over here. I'm going to plug in 3. 3 minus 2 squared is 1 squared. 1 squared is 1. So when 3 goes in, I get 1. If I plug in 1, f of 1 up here is 1 minus 2, and then you're going to square it. So f of 1 is negative 1, and then you're going to square it. Negative 1 to the second is positive 1. 1 goes in, 1 comes out. And then if you plug in 4, you get 4 minus 2, and then you're squaring. So f of 4 is behaving, after you plug in the 4, it's behaving just like 2 squared did. When I plug in 2, we got 4. Because when I plug in 4, I end up with 2 squared. I'm going to end up with 4. I plug in 4, I get 4. What's up here? Symmetry. To the right of 2, when I plugged in 3, I got a 1. When I went 1 to the left, when I plugged in 1, that's not negative 1, that's 1. When I plugged in 4, I get 4. That's 2 to the right. Here from 2, I went 2 to the right, I get a y value of 4. So if I go 2 to the left, 0. This y value is also going to be 4. It's that symmetry. Parabolas have symmetry. So when you compare the first graph to this graph, and again, apologize for my shoulder, but this is as smooth as it's going to get. This view graph is shifted. Everybody has taken a jump to the right. 2 steps to the right. That used to be a 1, 1. It's now over here 3, 1. This was at 0, 2. Now it's over here at 2, 0. This used to be at 2, 4. Now it's at 4, 4. This used to be at negative 1, 1. Now it's at 1, 1. This used to be at negative 2, 4. Now it's been shifted over here at 0, 4. Everything's been shifted to the right 2 units because of the minus 2. And the graph is now over here instead. You mess with the x's, you're going to have a shift. Now, do you see how it's -2 in there? And which way did it shift? Which way? It went to the right. You see minus, hey, minus supposed to go left. Well, yeah, technically. But you know what actually is in there is this. It's built-in negatives. You have to be aware of the basic equations. Move it up so it's not in the way. And I'm doing the horizontal before the verticals. A horizontal shift, C unit, and they're using C instead of H. I'm going to get to that in a minute. The horizontal shift, C unit to the right. If the original graph is h of x, if I replace this x with x minus c, then the graph is going to go to the right. Because it's a minus, it's going to go to the right c units. Because the c that we actually plugged in, it's a built-in negative. The formula has a built-in negative. So when we did x minus 2, what did I subtract? I subtracted a positive 2 from the x. It used to be an x. Here, it's a built-in negative. It's an x minus a positive 2. That's how I get x minus 2. If you see x plus 3, it's going left. Because the only way to get plus 3 is because it's x minus a negative 3. That's how you get a plus 3. The negative is built in. So you're going to do the opposite sign of the direction you see. Okay? Or you're going to do the opposite direction of the sign you see. But that's just on the x's. It's inside the parentheses. It's inside of the function. It's not the same for the y's. It's the x's. Horizontal shifts, opposite sign. Opposite sign. So for the parabolas, your parent graph right now, f of x is just simple x squared. The horizontal shift looks like this. F of x is equal to parentheses x minus, and I call it h squared. Inside that parentheses, that negative will always be there. Just like when you slope, it's always y2 minus y1. That's always x minus h. So when you need to figure out what the shift is, it's the opposite side. H for opposite. H for opposite. If I gave you f of x was equal to x plus 3, like I mentioned, squared. X plus 3, what makes x plus 3 equal 0? What value of x? Negative 3. So if I use negative 3, negative 3 plus 3, that's my 0 squared, and that's how I get 0. So negative 3, 0. So what used to be over here at 2, 0, what used to be over here at 0, 0, is now over here at negative 3, 0. If I plug in negative 2, x plus 3 is now negative 2 plus 3. So f of x squared. F of negative 2 is now positive 1 squared. F of negative 2 is 1. I used to get 1 if I plugged in 1 or negative 1. Now when I plug in negative 2, it's a 1. Over here it was 3. Okay, if I plug in -4, -4 plus 3 squared is -1, and then square it, and there's +1 again. At -4, we get +1. And then if you plug in -1, -1 plus 3 is 2, 2 squared. At -1, I get 4. Symmetry, if two units to the right of -3, I get a 4, then 2 units to the left will also give me a 4. If I'm at -3 and I go 2 to the left, I'm at -5, +4. Look at the graph and where it's at. It used to be at 0, 0, that's your parent graph. Now it's been shifted 3 to the left because of the +3. You do the opposite direction. I see plus, I'm going left. I see negative, I'm going right. But only for the horizontal shifts, only on the horizontal shifts. Built-in negative. The vertical shifts. What I'm showing you is true for all of the graphs that we're going to cover. So if you catch this for the parabolas, you will catch it for all of them. Here's our parent. And then over here. That is not in a parenthesis. I don't even see a parenthesis right here. It's after the parentheses. It's after the, sorry, it's after the square. It's after the square. So if we're making our basic parabola function, f of x is, you have a parentheses inside x minus h squared, then what comes after is what's happening right now. What comes after the square is what I'm talking about. So we're supposed to take all of these old answers, every single old answer we got, the 4, the 1, the 1 and the 4, and the 0. After we get those answers, you add 2 to the old y value. If I add 2 to all these old y values, starting with this vertex, it's going to take the old graph and it's going to move it up to here because 0 plus 2 is going to put it up here. Right at 2. This y value is a 1. Well, that y value should be down here at 1. When I plug in 1, I add 2, and it's now going to be up here at 3. When I plug it into 1 squared plus 2. That's been moved up 2 units. When you plug in 2 to the original, we get 4. If we add 2 to the last answer, 4 plus 2 is going to move it all the way up. When we plug in 2, we're going to get 6 now. All these old y values have been moved and pushed up 2 units. Symmetry over here on the other side, when I plug in -1, we would get +3. Plug in -2, we get +6. Parabola going this plus. Sorry. I mean, that Will Smith article. Robot movie. Okay. So this is my vertical shift. H is the horizontal shift because it moves it left and right. This too is a vertical shift because it's moving the graph up and down. Is it changing the shape of the graph? No. Still a parabola. Is it changing how wide it is or how narrow it is? No. Okay. So after the square is a plus k. It's a plus k. The h and the k together, this h and that k is the first point you need to find whenever you graph a parabola. And it's going to be the first point you want to find whenever you're graphing any of the things you're going to graph. It's the vertex of the parabola. Right here on the original parent graph, the vertex is at 0, 0. Well, look at this equation. F of x is just simple x squared. Well, it is also part of this this new function. F of x is parentheses x minus h squared plus k. So there is a number that was substituted into this for h and over here for k. And when we simplify, we just get x squared. So what happened from here to there, it was in between parentheses, the h would have had to have been a 0. Because x minus 0 is just x squared. And then since there's nothing added after that, then we would have added a 0 for the k. So x minus 0 squared is x squared, and then plus 0 is just x squared. So if you just have the plain old x squared, the parent graph, h and k are both 0, so the vertex, sure enough, is at 0, 0. That's a k value. There's no parentheses, so inside the parentheses, h would have to be a 0. H is a 0. K is a 2, so the vertex in this particular graph is at 0, 2. And right there's my vertex. So just like when you graph a line, y equals mx plus b, if you know what the b is and what the slope is, you know how to find all the points. If I know where the vertex is, I know how to get started to find the rest of the points. When we did f of x was x plus 3 squared, then inside here, remember it's the opposite sign, h was a negative 3, and there's nothing added, so k is a 0, and the vertex would be negative 3, 0. And that's where it was. It was right here, negative 3, 0. And it opened up. You have to be able to read the equation and take out the parts that you need. Take it apart piece by piece. So, get rid of this thing out of the way here. If I gave you and you had to sketch by hand, no calculator, g of x equal to parentheses, let's go with x minus 5 squared minus 8. Well, I know it's a parabola because it's a power of 2. So I'm going to want to find the vertex. So I need HK. So I'm going to write up here, go, what's the H in this equation, in this function? Positive 5, and what's the K? Negative 8. So my vertex is at 5, negative 8. That's the first point I want to find. 5 and then down 8, right here. And then it's going to be a parabola, opens up right there. Eventually on Tuesday next week, we'll come down. I need to plot at least 3 points, maybe more, for symmetry and accuracy. So I just want to pick one number. Let's just go 1 to the right. If I'm here at 5, let's plug in 6. 6 minus 5 is 1. 1 squared is 1. 1 minus 8 is negative 7. So when you plug in 6, we get negative 7. And again, because you want accuracy. That means if I go 1 to the right, y is negative 7. So if I go 1 to the left, if you're at 5, then 1 to the left would be 4, negative 7. Now, for accuracy, so that's got symmetry, but accuracy. Let's go 1 more to the right. If this is 5, let's go plug in 7. 7 minus 5 is 2. 2 squared is 4. 4 minus 8, negative 4. So if we plug in 7, we get negative 4. Plug in 7, we get negative 4. That's 2 to the right of the vertex. So if I go 2 to the left, the y value is also negative 4. 2 to the left is going to put me at 3, negative 4. There is my parabola. I had to find the vertex first, is where you start. Vertex first. Okay. And that's where you start with the absolute value. That's where you're going to want to start H and K for the square roots. That's where you're going to want to start with the rational expressions. That's where you want to start with everything. Where's the H and K? If you can find H and K, you're about 80% there almost. Okay. Finish up your 1-4 if you haven't. See you on Tuesday. Be on the lookout for the email that but be on the lookout for the email that has more assignment sheet. And if you didn't get your quiz, see me. Just the goal. Josh Aguilar. Jasmine. Francisco. Lewis. And Brian. Here. Marcelino. David. Here. Daniela. Los Rios. Here. Alma. Ryan. And Kelsey. All right. Have a great 4-day weekend. Remember, it was tomorrow or Monday. And then Lewis, I'm putting you down as a Zoom for anybody that does it by Zoom.
Okay. Thank you.
Have a good weekend.